Hi guys, I hope everyone is having a great weekend. Today we're going to talk about conservation of energy with friction. Now our other examples didn't take into account the amount of energy lost due to friction, so now we're going to start factoring that in. So now we're going to actually start talking about non-conservative forces. So you need to understand that the law of conservation of energy is still going to apply. We've got the increase or the decrease in energy, in the total energy of a system, is always going to be accounted for somewhere else. So here we have all of our possible energies that we've discussed: mechanical, thermal, chemical, and then this other down here, which are things like dissipated energy, like sound. So to transfer energy into or out of a system, you can do work on it. So if the only form of energy that's transferred into or out of the system is work, then we can say that work is going to be equal to the change in energy of the entire system. And this will come in play here in a second. I'll kind of show you what that means for an example later. So if an object is losing mechanical energy, let me go back. It's due to the fact that there's friction. So the energy lost by the object is equal to the increase in the thermal energy of the object. So this is kind of like what you experience when maybe you slide down a slide. You experience a little bit of friction, and the slide gets warm, and you get a little bit warm, and that's because thermal energy is being transferred between you two due to friction. The book doesn't like to say work due to friction because sometimes the friction may not be acting over the same displacement as the object. So sometimes the displacement for the friction won't be the same displacement that the object's actually traveling. So they don't like to use that terminology. I guess they just like to be really picky. So the total energy of a system that changes, right, is because we probably did work on it into or out of the system. And that's going to be equal to the change in the mechanical energy plus whatever it is that friction did, or the change in the thermal. So it's kind of a little bit easier just to get ourselves an example here. So on this one, it says Pete slides down a water slide and climbed at 40 degrees. So let's draw our 40-degree ramp. It says his mass is, let's draw him. Whee! Mass is 75 kilograms, and we've got a coefficient of friction between him and the slide as 0.35. So if he starts from rest at the top, way up here, which has a height of 10 meters above the ground, how fast is he traveling whenever he reaches the bottom? Okay. So the first thing we need to understand is that this is going to be a conservation of energy expression. So at the top, he has all potential, and that potential energy is going to get transferred into his kinetic energy at the bottom, plus whatever energy is lost due to our friction. So, in this case, we have mgh with height being our 10 meters as our starting potential energy. Now, we're not sure about his final velocity, so we're just going to leave that as a variable for now. But we need to figure out what his frictional force is here and the distance that that frictional force acts over. So our coefficient is 0.35, and that's equal to the force of friction over the normal force. Oops. And in this case, our normal force is equal to mg cosine theta. So our normal force is going to be 75 times the cosine of 40, and we're going to multiply that by 0.35. So that makes our frictional force be 20.1. Now it's acting over this S displacement, right, which is not the 10 meters that he's actually falling, but it's this side of the hypotenuse side of our triangle. So if we do a little bit of trig, 10 divided by sine 40, we get that our hypotenuse, or our change in S, is going to be 15.6. So, oops, this should be plus. So if I want to finish out my equation, this is my potential energy, kinetic plus 20.1 times 15.6. So we can, this is 7,500. That is 37.5 v squared, and then this is 20.1 times 15.6, which is 313.6. So now when we do our little bit of algebra here, we get a final velocity at the bottom of 13.84 meters per second. So this is a pretty straightforward example. It's very similar to some problems you probably would have seen last year in pre-AP. The only difference is that now we've got this term that we're tacking on to the end of it to describe the energy that's lost because of the frictional forces down the ramp. Okay, since everybody loves springs, we're going to do another spring problem. A couple of things that I noticed about our in-class bookwork the other day was that some of you guys struggle with getting the problem started, and so we really need to work on you guys developing a process. And I'm going to, at the end of this video, walk you guys through how I tackle problems, but it's just like any skill where you have to practice it and you have to be diligent at it, which means that you have to be doing your bookwork and you have to use the same process every time, regardless of the problem. So that's how it really gets to become habit. And that's how these problems that seem very difficult can actually become solvable and manageable because you're following a set process or a set of steps that you always do. So we're going to talk about that at the end of this video if you need that help setting up a process. Because I found as I was walking around that some people didn't even know how to start. And I really kind of felt that you should at least have that part down. Maybe when it gets into the trickier algebra, you get a little bit stuck, but starting the problem should always be something that you can do. Okay, so this is this question that I was kind of drawing out as I was talking, but we have a block that's hanging from a string, and this block is compressed by a spring. This distance that the spring is compressed is 0.3 meters. And the spring force has a constant value of 180 Newton meters. I'm sorry, the spring constant is 180 Newton meters. So we want to find the speed of the blocks after the 6 kilogram block is released, so the spring is going to extend. And the 4 kilogram block falls a distance of 40 centimeters. Bloop. So this is going to be 0.4 centimeters here. Okay. First thing we need to do that's very helpful is to draw a free body just so that you understand what's going on with your problem. For the 6 kilogram block, I have some kind of tension that's going this way, and then I have a frictional force that's acting on the 6 kilogram block. So this is my friction, and then this is going to be my tension, you can call it that. Also, the block that's hanging, I have the weight of that block, and then I also have the same tension that's being connected there. Okay, so once I kind of see what's happening forces-wise, now I need to see what's happening energy-wise. So where is my energy being stored at the beginning? Where is it ending up? So I can come up with an expression so that I can relate what's happening with my picture. So at the beginning of this, before anything moves or releases, I have a situation where I have all of my energy stored in this spring. The spring is compressed 0.3 meters. So initially, I have all potential spring energy. Because, and for the sake of this problem, since this guy is falling 0.4 centimeters, I'm going to take its resting point here to be at the 0 mark. That's going to make my life a whole heck of a lot easier, because there's no way that I could ever possibly tell how high this object actually is off the ground. So it's just going to make it easier for me if I set this 0 line here. So initial energy is all in the spring. The spring releases, these guys fly forward, this guy goes down. So at that moment, what is my energy now? Well, at that moment, now my energy is a combination of both the potential of this guy, and we'll call him M2, I think I've labeled him M2, and the kinetic of this guy. Or rather, the kinetic of the whole system. Because this guy, since he's falling a particular distance, he has both potential and kinetic at that moment, right? He's moving, and he's also falling. So he has both. So this M for our kinetic energy is going to represent the mass of the system. All right, so now that we know that, we can also start to talk about what's happening energy-wise. So energy-wise, we can also start to talk about what's happening friction-wise. So we have this initial energy here, and that initial energy is getting converted into this potential of this block, this kinetic of the whole system, as well as the energy that's lost because of our frictional effects. So if you guys don't have this copied down, copy it real quick, because I'm going to erase it, or pause the video so you can copy down the picture, because I'm going to erase some of this stuff so we have more room to work. So I know what's happening force-wise. I know what's happening energy-wise. So now I can go about trying to solve my problem. I'm going to rewrite this over here, if that's okay with you guys. Okay. Now I can say 1/2 kx squared, which is what I have in the initial conditions, is going to be equal to M2GH, the potential energy of that second block, plus 1/2 M1 plus M2 V squared, the kinetic energy of the system, plus whatever we lost when it moved a particular distance, when the frictional block moved S. Okay, so now we know enough from what they gave us in the problem that we can begin to just plug and chug from here on out. So we have 1/2. Our K value is 180. Our X value for this spring, remember, this X represents the amount that the spring is compressed. So the spring is compressed 30 centimeters, 0.3 squared. That equals to the mass of the hanging block, which is 4, times 10. And it's fallen a distance of 40 centimeters. So this is really the only time where you have to be careful, because we set that block when it was at rest, we set that to be the 0 point. So it's going to drop down. So that's going to be a negative 0.4 for the height difference. Plus 1/2, and then we're going to add those two masses together. That becomes 10 V squared. Okay, now the force, the frictional force, we have the coefficient of kinetic friction, and it's the 6 kilogram block that is sliding across that friction surface. So the frictional force then would be equal to our mu times mg for the 6 kilogram block. So that's going to be 0.2 times 60. And then that's going to be times the distance that the block slides. So if this 4 kilogram block drops 40 centimeters, then that means that this block that's resting on the surface gets dragged 40 centimeters. So that's going to be 0.4. So now we can just go about our algebra, and we get, for this side, 8.1 Ooh, that's difficult to do with that thing there. 8.1 times 10.4. And this is negative 16 plus 5v squared plus 0.2 times 60 times 0.4. And that's 4.8. Right, so 8.1 plus 16 minus 4.8. That gives us 19.3 equals 5v squared. 19.3 divided by 5, and then square root it. Our answer is about 2, 1.96 meters per second. Okay, so I told you guys I was going to talk to y'all about a process that I really need to see on all of your work, and I think it's really going to help you guys a little bit if you just get it in your head that this is what you need to do. So, as a tip for solving any physics problem, first step, always draw your picture of the situation. You guys learned this in pre-AP, and all of you guys are really good about doing that. Number 2, write your givens. Again, this is something we drilled in pre-AP, and you guys are really good at doing that. From now on out in this class, third step should always be to draw a free body. And if necessary, sometimes maybe it won't be necessary because the object's at equilibrium anyways, or whatever the case may be, but you need to draw a free body and write your net force expression for the x and the y direction. This is, again, a skill that takes a little bit of time. It takes a little bit of practice to get really good at it. But that's why I really want you guys to do it for every single problem, even if you think you don't need to. Because I think the more that you do it, the more you'll get in the habit, and the easier and easier it will become the more you do that. The fourth step from now on out in this class, since we've introduced the idea of conservation of energy, the fourth step is to write an energy expression. So similar to what I just did on the last problem, you need to talk about what's happening energy-wise in the problem that you're given. So tell me, where is the energy initially and where does it end up finally? Talk to me about the energy transfers that are taking place in that question. Now, once you've done these 4 things, hopefully something will stand out to you, or so hopefully you'll have an equation that you can start to solve. But if you still don't have an equation that you can start to solve, the 5th step would be to write down any equation that you know that has to do with, deals with the topics in the problem. So that means that if it's a kinetic energy equation or a kinetic energy question, you would write down everything that you knew about the variables that they gave you in the problem. And hopefully after that 5th step, there's going to be an equation that stands out to you and that you can start to begin to work with. Some of you guys are very hesitant to start working with equations if you don't have all of the numbers for them. And that's a habit that you need to break. I guess the 6th step is not really a step. It's really just a tip. It's okay to work with incomplete equations. It's okay. If you say, okay, well, I know this problem has something to do with springs. So I know I'm probably going to need to know my spring force equation. I'm probably going to need to know my kinetic energy of potential energy of a spring equation. The spring's moving something, so maybe I'll need to know my kinetic energy of a spring equation. Kinetic energy equation, rather. But it's okay to start playing with these and plugging things into one another, even if you don't think that it's going to work out. I think you noticed today when I was walking around that I said I was saying things like draw me a free body, write me a net expression for your forces. Okay, let's talk about the energy, what's happening with the tension here. So sometimes you really just have to play with the formulas until the inspiration strikes you and you can have that aha moment. And like I said, it takes a lot of work and it takes a lot of practice. And that's why I'm really trying my best to help you guys out in class when these problems come up, so that you guys can get some help the first couple of times that you do them. But it is going to take a little bit of practice, and I promise you you'll get it. But for now, I would say focus on these 6 things. Make sure that you're doing them for every problem that you don't know how to solve. And I really think it's going to help you guys a little bit to at least get started on the process. And that is the video for tonight, and I will see you guys on Monday.